Once upon a time, scientists and mathematicians and philosophers had a bias whenever they would look out at nature. They felt like it had to have symmetry. In other words, the planets couldn't go around the sun in elliptical orbits. They had to be perfect circles. Now, when it came to numbers, the fact that you could take the square root of positive numbers, but you couldn't take the square root of negative numbers, in fact, what would that really mean? Bothered early mathematicians. They were like, nah, symmetry is broken there. You need to be able to do the same thing to the positive numbers and the negative numbers. And so somebody decided they would make it happen. And so they invented imaginary numbers. Now, I'm sure some of you are like, I have enough trouble with real numbers. I don't need to deal with imaginary numbers too. But it turns out that there are actually very practical uses for imaginary numbers. Nothing less than they help us make equations for alternating currents. Now, of course, when a lot of this was done, there wasn't much understanding of electricity or wires or any of that sort. It just goes to show you sometimes the math is way ahead of the science, but they did create imaginary numbers. Now, let's start off with the definition. A complex number has two parts. A, the real part, just like any ordinary number, and B, I, the imaginary part, where the I is the square root of -1, by definition. Now, sometimes when we solve a quadratic equation, and if you're like, well, I don't remember what a quadratic equation is, that's anything that has like an x squared plus an x minus 5 or something like that. It's got a squared term. In solving them, you might not get any real solutions. In other words, if you were to make a graph, it would not show up on the graph at those points. However, we can still find those solutions. They're just not real ones. No real solutions bothered those early mathematicians. And so they created the imaginary ones. I equals the square root of -1. Now, interestingly, if you start multiplying I times itself a number of times, you see an interesting pattern. I squared equals -1, which of course anything that's square rooted times itself, which is also square rooted, basically undoes the square root part, and so you get -1. If you have I cubed, well, that's really just I squared times I, and we've already said the I squared part is -1, so this is -1 times I, or -I. If you do I to the fourth, well, that's I squared times I squared, which is -1 times -1, which is a positive 1. Well, here's the thing. Those are the only 4 values we will get for any exponent involving I. So I to the 5th, I to the 4th times I, ends up as just being I. I to the 6th ends up being -1. I to the 7th, -I. I to the 8th, I. And in fact, you can generalize this, and really the simplest way is, if the exponent is divisible by 4, a multiple of 4, then the answer is 1. If the exponent is any other even number that's not divisible by 4 evenly, your answer is -1. If it is between those two, in other words, it's an odd number, but it's 1 more than, or this is 1 less than what would have been a multiple of 4. So for instance, 3 and 7 and 11, those are all 1 less than a multiple of 4. your answer is always negative I. And if it's always one more than a multiple of 4, like 1 and 5 and 9, then your answer is always I. Now, two complex numbers are equal if the A part and the C part, the real parts in other words, are both equal, and if the imaginary, the B and D parts, are both equal. If that is true, then we can say the two complex numbers are equal. If we want to add complex numbers, we add the real parts together, so the A and C, and the imaginary parts together, the B and D. If we want to do the difference, we subtract the real parts and we subtract the imaginary parts. And so here you have some examples. 3 plus 5i plus 2 plus 4i, the 3 and the 2 give us 5, 5 and the 4 give us 9, and so our sum is 5 plus 9i. If you want to do subtract, the 3 minus the 2 gives us 1, and the 5 minus the 4i gives you just I. Note that a complex number, again, always has two parts. We generally write the real part first and the imaginary part second. It is, of course, possible to have just the first part. We call them real numbers, the numbers we normally deal with. It is also possible to just have the second part. In other words, all we have is the imaginary part. If we're doing multiplication, essentially we are foiling. You might remember the term FOIL, first, outer, inner, last. Basically, the first is the A times the C part. The outer is the A times the DI part. The inner, the BI times C part. And then last, the BI times the DI part, which written here is just a matter of distributive property all the way across. So the A times both of these, the BI times both of these. And then again, you distribute one more time, you end up with this. Should point out, however, that I squared is negative 1. So that will actually be a number. The AC will be a number. The parts with the I's will be imaginary. And so in the end, you'll end up with something in which it's the difference of the outer and first and outer parts, and then here the inside parts. So for example, just doing distributive property all the way across, 2 times the 4 gives us 8, 2 times the 5 gives us 10i, 3i times the 4, 12i, 3i times the 5i, 5i squared. The 10 and 12 gives us the 22. We already had the 8. The 15 turns into negative 15. 8 subtract the 15 gives us negative 7. Now, if we have the special case in which the A parts match and the B parts match, except one is positive and one is negative, when we go through the process, we end up with an answer that has no imaginary part. When that happens, these are called complex conjugates, and it's one way for us to essentially get rid of the imaginary part. If we are doing division of imaginary numbers, what we have to do is multiply the top and the bottom by the complex conjugate of what's ever down there. So note, if this is C plus DI, then this is C minus DI over C minus DI. If that one was C subtract DI, then these guys would both be pluses. We do our same little distributive property that you see up there for the top part, but the bottom part is just going to end up being C squared plus D squared. Because remember, we have a subtract here, and then we have an I squared as well, so that's going to cancel out the subtract symbol, and we're going to add up with an add. So for example, here we have 2 plus 3i over 4 minus 5i. So to do the division, we multiply top and bottom by the 4 plus 5i. Here, we'll end up doing our distributive, again the 8, and then the last parts will give us 3i and 5i, which is 15i squared, which gives us the negative 15. The outer gave us the 10, the inner gave us the 12. We did that one up here. And so we have our minus 7 plus 22i, just like we did up here. But the bottom is just going to end up 4 squared and 5 squared, which is 41. And so there is our answer. Likewise, here's another one in which the top part doesn't have any imaginary part. But again, we want to get rid of the 1 plus I in the denominator. And so we multiply top and bottom by the 1 minus I. It's complex conjugate. We end up with 1 plus 1 in the denominator. We have 2 times 1 minus I in the numerator. The 2's will cancel, leaving us with just 1 I. And you might say, well, why would we want to do this? And you might remember, or not, but we have a rule for any radicals, any square roots kind of problem, that you can't leave them in the denominator. And since I is technically the square root of negative 1, we can't leave any square roots in the denominator. And so we have to go through this process of rationalization to make it so that it's just any square root or cube root or whatever is in the numerator. All right, so let us look at some examples. And when dealing with things like square roots, one of the things to do is to split it into 2 parts. The part that you can take the square root of and the part that you would not normally think of taking the square root of. So here, negative 49 is the square root of 49 times the square root of negative 1. That gives us 7. That part, by definition, gives us the I. And so that is our answer. That is the simplified form of the square root of negative 49. Now, sometimes they are not perfect squares. And again, I'm going to split it into parts that are squares. So 16 goes into 48 3 times. So by the way, when dealing with square roots, if you can do the factors, that really helps. One way to do that is with what's called a factor tree. A factor tree can look like this. One way to do that is you simply, all right, that's cut in half, 24 and 2. Cut in half again, that's 12. And 2, that's 6 and 2. And that's 3 and 2. And so right here and right there, that's 2, 4, 6. So that gives me the 16. 2 times 2 times 2 times 2. And then we also have the 3. So there's my 2 factors, 16 and 3. And so I have the 16 and the 3. And then, of course, I have the negative 1. So that'll give me 4. The negative sign out front stays there. It doesn't go away, and it doesn't go inside. And then I have I and the square root of 3. Now you might say, well, why didn't you write the I last? And generally, I like to write the I before the square root symbol, because otherwise I might accidentally, if I'm not careful enough in my penmanship, think that the I was actually inside the square root symbol. And so by writing it here, I make sure and keep that straight. So anyway, getting from regular square roots to answers that have I's in them. All right, so now let's look at some simplifying. I to the 31. Well, that's I to the 28 times I squared times I. Notice how basically I'm just adding up my exponents. 28 and 2 and 1, that's 31. Now 28 is divisible by 4, so that's a 1. I squared, well, that's a negative 1, and then I have an I. So this is negative I. 100. 100 is divisible by 4. So this is just 1. 234. 234 is not divisible by 4, but it is an even number. So I know that's going to be -1. Now, I could have gone, well, that's I to the 200, and then again, I to the 32, and then I squared. So that would give me a 1. This would give me a 1. That would give me a -1, and there's my -1. All right, now we're going to add a couple. So again, first part's without the i's. Second part with the i's. Final answer, 7 plus 3i. All right, now we got parentheses and we got subtract, so we got to keep our signs straight. So let's just do all the ones that don't have i's first. So a 4, subtract a 2, plus a 2. So all of that will be the real part. And now the i's, -5i, subtract another I, plus a 5i. And of course, -2 and 2 will cancel, -5i and 5i will cancel, and it leaves us just with 4 subtract I. All right, so here we have 2 plus I cubed, which means we're doing 2 plus I times 2 plus I. Now, if I put these two together, in fact, let's go ahead and flip the page and do it there so we have a little bit more room. 2 plus I times 2 plus I. So 2 times 2, that's 4. 2 times the I, that's 2I. I times the 2, that's 2I. I times the I, that's I squared. So 4 plus 4I plus I squared, but the I squared is -1. So 4 plus 4I minus 1 gives me 3 plus 4I. So now I'm going to have the 3 plus 4I times another 2 plus I, because remember we had 3 of them. So 3 times the 2, that's 6. 3 times the I, that's 3I. 4I times the 2, that's 8I. 4I times the I, 4I squared. So 6 plus 11I minus 4, because again that I squared will be a -1. 6 minus the 4 is 2. And I end up with 2 plus 11I for this one. Now, in the second case, notice that I have complex conjugates. So I'm going to do it the long way first. 5 times the 5, well, that's 25. 5 times the -4i, that's -20i. 4i times the 5, that's plus 20i. And then 4i times the -4i is -16i squared. And of course, one's negative, one's positive, so they cancel out. I'm left with 25. Subtract a -16, because the I squared turns the 16 negative, and so that becomes 25 plus 16, or 41. Now, the other way, which I could mention, we have them up here as our example. 4 minus 5i, 4 plus 5i is just the sum of the two squares, 4 squared and 5 squared, just like we got 4 squared and 5 squared. All right, got a couple of divisions. Quotients go with division. So I'm going to multiply top and bottom by I, because again, we can't have any square roots in the denominator. So the numerator becomes 3i plus 4i squared. The denominator becomes I squared, which means I have 3i subtract 4 over negative 1. Because again, the I squareds are negative 1s. And then to write it in proper form, that's going to be 4 subtract 3i. Now in the second one, we need to use the complex conjugate. So 3 over 4 minus 5i times 4 plus 5i over 4 plus 5i. Now, we've already done the 4 minus 5i and the 4 plus 5i's. We did them right above. So we already know that that's going to be 3 times 4 plus 5i over 41, which, if we wanted to write it in proper form, 3 times the 4 is 12, 3 times the 5 is 15i, and then each one is over 41. Now, one thing to check is if the denominator and whatever factor is out here, I could do some canceling. In this case, I can't. 12 and 15 don't go into 41. But let's say that that had been 42. Then I could have canceled the 3 with the 42. And I would have had 4 over 14 and 15 over 14 instead. All right, in this last one, it says show that this is a square root of I. Well, what that means is if it's a square root of I, then that means that this should be true. Because when I'm saying it's a square root, what I'm saying is if I take a square root of this whole thing, and then of course I square it, I should get back whatever it says I'm supposed to get back. All right, so let's check this one out real quick. I'm going to do it on a separate piece of paper. Root 2 over 2 plus root 2 over 2i. And I need to square this. That's basically how I'm going to show that just one of them is the square root of I. So, first times the first in each one, root 2 times root 2 will just be 2. On the bottom, 2 times 2, that's 4. Then the outside one, root 2 times root 2, again, is going to be 2. And then 4 on the bottom, but this one has an I. In the middle here, I have root 2 times root 2, that's 2. Over 2 times 2, that's 4, but it's also got an I. And then the last part, I'll have root 2 times root 2, which is 2. And again, I have a 4, but the 2 i's give me an I squared. Well, these two guys, 2 fourths and 2 fourths is 4 fourths. And this is going to be 2 fourths. But this one is going to be minus 2 fourths. Which, of course, those parts will be gone. And 4 over 4 is just 1. In other words, I have shown that, in fact, this is equal to the square root of I. And so that does it for section 3.